Welcome, everybody. Thanks for coming to share your Friday, or actually not even Friday, it's Wednesday afternoon lunch with us. It's pretty amazing. I really didn't expect such a big crowd. And actually, I guess this is a very interesting topic for everybody, so thanks for joining us. My name is Robert Chow. I'm the product manager for two of the lesser-known, lower-profile services within AWS, SNS and SQS. But nonetheless, these are very important services for Amazon and AWS. And so it's been a really busy year for us. We have a small team in Vancouver developing these products for SQS and SNS. And this team has done an amazing job throughout the year. And in fact, this year, we released server-side encryption, VPC endpoints, and then we've also started rolling out more FIFO regions for SQS. We recently rolled out Tokyo and Sydney. And then now we also released a message filtering for SNS, and also SQS as an invocation source for Lambda. And actually, that was one of the more higher demand service features that was requested by our customers. And after rolling that out, we actually got a lot of questions from people asking about how do you use these in sort of the higher throughput and kind of bursty type applications. So we thought it would be a good idea to put a session together with this and sort of give everybody sort of a general understanding and diving deeper into a little bit of the best practices there. And so we've also invited a couple of our customers here, Christian Garcia from LetGo and also Luca Di Lieto from NL. They'll be sharing their experiences with us today as well. So let me get started then. So we're all human beings, so we do things on a schedule. We eat at the same time, we go and sleep at the same time. And then with a lot of us, we actually went and did a lot of shopping recently. You know, we went to do Black Friday shopping and Cyber Monday shopping. So that really creates a big peak. So that's lots of traffic comes all at once. And sometimes that traffic can be 2, 3, maybe 10, 20 times your normal traffic rate. Then after you do all the shopping, then inevitably, you have to pay for your bills. So everybody goes and pays their bills dutifully. Sometimes you do a credit card transaction, you do it right away. Sometimes you go to a bank and you pay it on payday, and then that gets posted. And after Christmas time, I don't know if you have kids, but I have 2 daughters, and they watch the Kardashians religiously. And so they're always wanting to know what happened to the Kardashians after Christmas time. So no doubt after Christmas time, everybody will be rushing to publish their stories about the Kardashians. Maybe it has to go for editing. Maybe it has to go for translation. And that creates really burst a lot of traffic. So one of the problems with traffic patterns of this nature is that it's really hard to plan and provision for that. So you might end up planning and provisioning resources that actually don't get utilized most of the time. So you're basically pouring money away at that point. On the other hand, if you don't provide enough resources and don't provision enough, then you could be potentially turning away a lot of customers because they simply can't access your service, or they'll be going to a different competitor. So one of the things that you should add in the toolbox is within AWS, we've been developing serverless technologies. And one of the properties of serverless technologies is that there's actually no infrastructure for you to buy, provision, manage, or configure. So we provide all that. That's one of the property number one of a serverless technology. The other one is that the security is built in, at least into the hardware layer and all the service layers. We provide the security for that. We look after compliance for you that. Of course, the security of the application itself, that's your responsibility, but the underlying security is done for you. And then the other thing is really around bursty traffic. So scaling up, our services will scale up and down according to your usage. And the best part for you as the customer is that you only pay for what you actually use. So you don't pay for a lot of idle resources. So within AWS, we have a modern application development platform. So we've been assembling a lot of these services. And this is basically shows some of the services that we've assembled. It's not everything, but has a lot of what we have. There's actually another talk that I'll show you which session it is. And that talk is more of a broad base, and it talks to you more about each of these services in this diagram. But basically, we have services that give you serverless compute, database, service integration, developer tools, and also for monitoring and security and compliance. In this session, we'll focus on AWS Lambda for compute and integration with SQS and SNS. So SNS. So SNS was actually launched in April 2004. So it's one of our oldest services. It's basically a pub subservice. Basically, you publish to a topic, and SNS takes care of fanning that out simultaneously to multiple inputs. So it's a pub service that does that functionality for you. And then SQS is a queuing service. So for a lot of our customers, they use that to build decoupled and scalable services, basically decoupling microservices and application. So the property with both of these services is that they're both very simple to use. They're highly reliable and durable. So for instance, every message that gets put into SNS or SQS is actually replicated and held across multiple geographically separated availability zones. So it's highly durable and available. And both of these services can adapt and scale to your service with very high throughput. So that's a really key property of these ones. You don't have to provision any resources, they just scale up. Some of you might have heard of a small company called Amazon. And if you've ever ordered anything from Amazon, there's a pretty good chance that what you ordered, your transaction actually went through one or both of these services. So that's how critical these services are. Lastly, there's AWS Lambda. So that's one of the newer services out of this bunch. And basically, that gives you the ability to run your code without having to worry about provisioning servers. And you can basically run them and use them. And you can only get charged for the Lambda functions that you actually use. So let's go and dive into a little bit of how these services are used. Looking at event-driven architecture, this is a very common pattern for the customers that we have. So basically, if you go from left to right, events are generated. It could be user-generated events or from another system. These events are published to a topic within SNS. And SNS takes care of fanning these out for further downstream processing. In the very top, you see that it's fanned out and processed to a Lambda function. On the bottom, you'll see it can go to existing servers to an HTTP endpoint. Or our newest feature is going through an SQS before processing by a Lambda. SNS, of course, can also drive to endpoints that are more user-centric. For example, it can drive notifications to SMS messages, mobile push to phones, and even email. But for the purpose of our discussion, we'll focus on sort of the system-to-system applications. So the two new features that we'll talk about today are SNS message filtering. And then we'll also spend time looking at the SQS to Lambda implications. So let's dig into the event distribution portion of that. So the events could be a customer order, for example. In the case of SNS, we actually have native integration to a lot of event sources already. So if you're familiar with things like CloudWatch or S3, we actually have native integration to over 30 event sources within AWS now to SNS. So in the case of CloudWatch event, it might be an alarm that generates a message. And that message then is fanned out by the SNS service. And it can fan out up to 12.5 million subscribing endpoints per topic. Nobody actually goes that high, but that's what our system allows for. And then if you look at this pattern, basically it's a broadcast pattern right now. And so each of these messages get fanned out each of these endpoints. And on your endpoint, you're basically you're processing each of these messages. And in most cases, if you intend to broadcast this message and it's meant to go to every single endpoint, that's fine. But there are many cases where you actually want to be more targeted and only have message go to certain endpoints. Previously to our message filtering capability that we added, you might have had to write code to kind of filter out your own messages and discard the messages. The problem with that is with a heavy load, you're really utilizing your resources heavily. You're probably wasting a lot of money as well. The other solution people have done is that instead of they've actually looked at adding topics. So the other way to sort of direct your traffic is to add topics. So having your publisher direct the traffic to a topic and having subscribing endpoints that are attached to only those topics. That's really, it's workable, not that ideal. And the reason it's not that ideal is because you really want that sort of abstraction layer, separating your publisher from knowledge of your subscribing endpoints. And that's kind of what message filter allows you to do. So message filters basically allow you to, in essence, tag the messages with key value pairs. And then based on those key value pairs, your subscribers can filter out and decide which messages that they actually want. So what that does now is it allows your processor really focus and only process the messages that you care about. So we'll save you a lot of processing and a lot of expense as well. So with message filtering, it's actually completely integrated with our cloud function, CloudFormation service, so you can deploy your services in a consistent manner. And you can, once you're deployed, you can also use CloudWatch events to monitor the number of messages that are being filtered out. So what happens when you start dealing with a really bursty load? So a lot of times you're kind of steady state really low, but in these peak periods you actually deal with a very heavy load, some potentially during these peak periods. So the first thing that you want to pay attention to is the throughput. So on our website, we publicly state some default limits, and you want to pay attention to those limits. Basically, it's not that we can't support higher limits, but we put that to let our customers know that that's the limit that we'll allow by default. And what happens is kind of a lot of our customers, and we get instances where customers, maybe they're doing something new, they haven't tried the service, or something has actually gone wrong with the way they've been processing things, and they actually get spiky data and lots of traffic through that. And rather than wait for them to find out at the end of the month with this really nasty large bill, we actually prefer to set these limits, make sure that the customers are throttled, and then we'll reach out to those customers, make sure that they're actually intending to have that high traffic, and then we'll allow that on a case-by-case basis. So it's really making sure that our customers are not surprised. But if you already know that you're anticipating a large throughput, make sure that you reach out to us and say, hey, I'm going to get higher than your limits. Let's talk about that situation. And with high traffic, you're going to be concerned about latency. So one of the things that we allow, although we allow a high fan-out ratio up to 12.5 million, if you're really concerned about latency, the latency does change a little bit as you go up to higher and higher fan-out ratios. So for really high fan-out ratios, such as say 30,000, is what we default our soft limit default in US East 1. In that case, if you're actually intending to go 30,000, you want to keep the number of subscribers per topic to under 10. But in a case where you're actually only maybe going at 300 transactions per second, you could attach up to 500 endpoints. Most customers usually most cases are under 10. And then lastly, you want to consider how you're utilizing the filters. So we have a soft limit of about 200 per account. And that's for most accounts, that's more than enough. But however, if you find a situation where you do need more, that's something we can accommodate. So now let's turn our attention to event processing. So if you remember the diagram that I showed you in the beginning, which is basically event-driven architecture, and you see that it kind of forks out the processing. So there was an HTTP endpoint processing, there was SNS to Lambda. And so this is our newest feature, so we'll spend time focusing on this. And this is basically SNS publishing notifications to an SQS queue. So in this case, what happens is that the message goes into an SQS queue, and it's held there for processing by the Lambda service. So the Lambda service basically will pull that queue and take the message off and pass it to the Lambda function for processing. And once the Lambda function is finished processing that message, the Lambda service will then go and remove that message from the queue. In the case that the Lambda function takes too long or doesn't process it in a timely manner and doesn't actually remove the message, then we have something called a visibility timeout in the queue. And what happens there is if the message isn't removed, and then it goes back in the queue for reprocessing by another function. You could see that you could get into a situation where that happens over and over again. So we have the capability, if you actually process and you keep processing the same message over and over again, after some count, we give you the ability to sideline that message into a dead letter queue so you can reprocess it, make sure that everything's working, then reprocess that. So if you look at what happens in the event, there's a really heavy bursty mode. So as I mentioned, SQS really scales up and allows you to absorb all that traffic. And so whatever you can throw at it, it'll just absorb it and keep it in the queue in a durable manner until you're ready to process it. And what Lambda does, it scales up the Lambda functions up to some concurrency limit. So you're allowed some concurrent number of Lambdas, concurrency units to process that. And at some point, it will scale up until it hits that limit. So why would you want to control that limit? Well, one thing is you probably want to be careful with your costs. You probably don't want your Lambda functions to go crazy and end up with a big, huge bill. The other reason is that you might actually want to control the rate. So for example, if you have a resource, maybe it's a database or another system downstream that can only tolerate certain processing rate, you want to use your concurrency limits, sort of throttle that and make sure you meter that traffic out. Lastly, you can also use that as a sort of a kill switch. So if something really goes wrong, you can actually set the concurrency limit down to 0 and effectively stop that processing until you resolve the issue. One of the more interesting applications that I've seen through some of our customers use is they actually use SNS message filtering in conjunction with SQS and Lambda. So what they do is sort of a priority scheme. So they might have one queue that processes at higher priority, giving much higher access to certain types of traffic to this precious resource. Another queue at a lower priority, and sort of limiting that access to that resource. So for example, if you're a bank and you have some transactions, so you obviously want to take care of the real-time transactions right away, so you would route that to your higher priority queue and service with higher number of Lambda functions. And then for something that's more of a batch, then you would sideline that and let that go to a lower priority queue. So a few words just to help you understand what happens when you start processing Lambda functions when it's invoked by an SQS queue. So the first thing is that the Lambda service will start with 5 concurrent functions. And then it will scale up 60 concurrency units per minute. So the consequence of these two numbers is that first, you don't want to set your concurrency limit to less than 5, because if you do, then you might end up with a lot of throttling. The other thing is if you're actually using VPC endpoints, VPCs, then you want to make sure that your EC2 rate limits don't restrict you from scaling up at 60 units per minute. So what happens is that Lambda actually will start to pull a queue. So when there's no messages in the queue, it will pull every 20 seconds. And then as soon as a message arrives, it will actually deliver that right away. And then depending on how much traffic there is in the queue, it would pull more and more often, increasing your throughput. The other way to increase your throughput is you can use message batching. So you can batch up to 10 messages into a single batch, and then you can process that as one concurrency unit. The other thing that to note is the code starts with Lambda. So when it's the first time that your code is actually being invoked inside a Lambda, it actually takes time for the Lambda service to create the context, download your code, start a new function context, bootstrap the runtime, and then actually run your code. So code start usually happens only at the beginning. So when you're in steady state, you don't really have to worry so much about the code start. It's only at the beginning. But in a case where you're actually really concerned about that latency, this is something you do need to pay attention to. So it's a pretty in-depth topic. We're not going to be able to cover it here, but I'll point you to, there's a lot of material and even reInvent sessions on the topic. And one of the ones that actually was last year, it's called Becoming a Serverless Black Belt. And that's a really good session. It talks you through some of the intricacies about what you need to do to Lambda to kind of mitigate the response and make sure that you're addressing this. There's another thing that you should know about Lambda is that it's actually stateless. So unless your function and your message are self-describing, and if you're dependent on carrying on state, you might actually have to go to a database and retrieve data before you can actually do something. So that adds additional time. So that's something called, you may hear later in some of the other sessions, called state hydration. So that's something else you need to and should be aware of, especially when you're really depending on something to ramp up very quickly in a bursty situation. Now, before I ask Christian to come on stage and share his experience with our services, I'd like to just close up and talk a little bit about the two processing points paths that I showed you in the beginning. The one was SNS straight to Lambda, and then there was SNS through a SQS queue and then to Lambda. So how do you decide which one to use? So one of the first question is that is your downstream able to absorb the traffic that you're giving to it? In the case of going to Lambda from SNS, if your downstream service can handle that rate, then that's probably a good way to go, because it'll save you the latency through going through a queue. It'll save you the cost going through a queue. But in the case where you actually need to rate limit that because some downstream resource, then your best option is go to SNS, to an SQS queue, then eventually to Lambda. The other thing you should be aware of is how are messages deleted. In the case of SNS to Lambda, once SNS delivers that message to Lambda, it deletes it. So in the case if your Lambda function does not process it, that message is lost, because SNS effectively says, I'm delivered it, it's gone. In the case of, with a queue in there, the Lambda function actually has to complete, and then the message is deleted. So you can be sure that that message was actually processed downstream. So it's a little bit more secure in that way to make sure that if you're counting on every message is being processed. And then in terms of the retries, in the case of SNS delivery to Lambda, if the Lambda function's not there, it will keep trying up to 13 hours. But in most cases, that never really happens, because usually, the Lambda function's all there. So that's very rare, but it's something you should be aware of. But in the case of SQS, we have the option to store that message for up to 14 days before it's removed. So, whoops, pressing the wrong buttons here. So at this time, I'd like to invite Christian Garcia up on stage. So Christian's the VP of Infrastructure at LetGo. LetGo has over 100 million downloads, and one of the biggest online websites where you can buy and sell things. So, Christian, welcome.
Thanks, Rob. Hi, everyone. I'm Christian Garcia. I'm the VP of Infrastructure in LetGo. And what I'm showing you after the small introduction of the company, what I'm going to show you is a piece of the LetGo's history, and mainly how we moved from one of the most common architectures to a new way of understanding how we move the data across all the services we have. LetGo, in global terms, is a company with more than 100 million of downloads and more than 400 million of listings. Is the biggest and fastest application for buy and sell locally in America. So, as one of the America's most popular apps, the LetGo's marketplace is filled from everything, from cars, collectibles, furniture, electronics, and anything you can imagine. With innovative features like image recognition, video posting, and LetGo Reveal, the LetGo's marketplace offers to you a lot of things for at least what you need and free great deals near to you. Listing something is as simple as checking a picture, given the LetGo's technology suggests a price, a title, and a category. More insights, technically within the company, we're handling bunches of data as shown. This means that it's a transition between a small company to a big huge of people in LetGo that is handling tons of data. And as a consequence of that, we're data-oriented. That means that we are checking our decisions based on the behaviors and trends of our users while they are browsing the application. And we are squad managed. That means that each team is totally independent of and autonomous for developing its service, because all the hands and brains are assigned full-time within the squad. More in depth, in technical area even more, in terms of transaction and usage, in the global area, during our first 3 years, we have experienced a huge usage of the AWS services, given our requirements were mainly based on the massive usage of the cloud on their scaling capabilities. More specifically to the SNS usage, this is an example of what they say. We took SNS and pushed it to the limit for making possible all the stuff. But when we generated AWS, not everything was just as easy as taking our existing services and plug and play it within. So these kind of situations made us to reinvent ourselves. And as a consequence, we had API REST services for moving the data across the services we had. This is an example. Initially, when we were using REST APIs, everything was nice because we had a small environment compared to now, and just a portion of the traffic we have now. Everything was perfect, was a better process, until we started to grow extremely fast. As a consequence, we had to deal not just with the external traffic, but also with the internal traffic generated by ourselves. So the main chaos generator was our own environment. One of the major issues we used to suffer was when one of the main cores of the company was down. As a consequence, all the services that were needing that core service were also down. And all the data sent during that period of time was lost. That means a drama. The constraints we had in the past. In the infrastructure area, we had the latency. Given the traffic is HTTPS, you have an overhead in terms of latency that is increasing even more when you are adding layers underneath. In the spikes, scaling the HTTPS services is a big challenge. So as well as you are as weak as the weakness part of your chain, you have a problem. So if you cannot handle it ever, look for another solution. And the other part is the money matter. It's affordable cost. Probably you can afford to pay 10% more of service in your external layer. But having this kind of decision in all the services all the time is to burn the money. So look for another solution. The data loss, that's really clear. A service under that conditions, if it's down, we have a problem. In the coding area, we had the complexity of developing a specific HTTP code. So if we never needed an HTTP solution just for storing data or apply some logic routines for storing that data, why we were using it? And the no microservice stable option, that's a consequence of the complexity. So we were limited by how many pieces we can divide the puzzle. So in front of that situation, that chaotic situation, we decided to move to a domain-driven architecture. We divided that migration in 3 phases, and you used 3 main statements. In the statements part, we had each service published in its topic. The main key for developing a domain-driven architecture is to set a source point for broadcasting the messages. At this moment, the service that want to do that, just raise the hand and say, hello. The other side of the architecture is the subscription, where the service interested in another service information just need to create a set of queues and subscribe it to the topic is interested in. And the projection. The projection is the data part, or the storage part. That means that given any service can hear information or store information of any other one, it's important to maintain a small subset of information of the other ones. So this way we prevent the services to ask information among themselves. And in the migration, the first one was only SQS sending messages across all the services we had. This can be nice when you have a small environment. But having to use that with more than 50 services and more than 800 different kinds of events can become a headache. The second one was the SNS subscribed to SQS queues. This is better, but not best, because the ratio of discarded message was expensive and not efficient. And the third one was SNS plus SQS plus the filtering, where only the needed message is going to be assigned to the specific queue, and the queue usage is optimal. And this is the result of our migration. Seems quite similar to the old unstable one, but it's far away. Given the external layer, it's most focused on receive the external request and processing that for sending the events. And the internal layer, it's focused on processing that messages and generating new ones. Basically, it's all about the messages. What's going to happen when an internal service is down? In that case, the external layer service will be sending the messages to the queue that is going to be storing the messages. So we can solve the problem of the data loss. Why? We decided to use filtering. We thought in the past, for each message that was published, we had to check and waste our time and resources checking if the message that was in the queue was the correct one, otherwise was discarded. If you apply this to tens of services, doing that to millions of messages per second, we have a nice system for discarding messages, but a really slow and expensive one for processing the correct ones. And with the present. Thanks to the SNS filtering, the destination servers will get only the message expected on the queue is assigned. So we don't need to waste that services and waste the money for checking if the message is correct or not. Given SNS filtering do the work. The real world results. In the part of the money, we have SQS and SNS savings. In the EC2 part, we have more effective time processing than discarding the message. And we have a fine-grained level of scaling according just for the type of message. On the part of SQS, we also experience a huge decrease too. Even the messages delivered on the queue are only the expected ones. And also we have the effectiveness processing, because the 100% of the message in the queue will be the correct. We don't need to discard it. And you don't need to depend on APIs, because all the messages are delivered near to instantly, everywhere. More about the money. The cost evolution. That's the cost evolution of the first service we migrated from API to SQS plus SNS during all the stages. As you can see, during the first phase, the cost of EC2 was really, really huge. But when we migrated to the second phase with SQS, we experienced an important decrease in that cost, and even more during the third one. Given the SQS and SLS filtering was really, really fine, and figure out that in that service, all the traffic was growing constantly. So it's a huge kind of save. Recommendations based on our experience using that. In the compute area, just squeeze your instance. You know how far can you go with your server. So don't worry about if your server is at CPU of usage, because the main goal for you is to keep your queue void. In the scaling, more than the CPU, as I said just now, take a look to the number of messages available in the queue. So will be your main objective for keeping your services on time. The Lambdas. The serverless functions are an extremely powerful tool that can smash your database storages. So first of all, check if you can handle a Lambda scale-up process. The dead letter. The letter command equal to rewrite policy. If a message cannot be processed after 5 attempts, send it to the dead letter and check where is the problem. So probably it's going to be any other place. And the data loss. All the messages are going to be there if an internal service is down. So just focus on keep up and running your external layer and your storage service. And that's all. Thank you, everyone.
I guess, Christian, one of the things I was wondering is if you can share with the audience, how long did it take you to migrate from your original approach with the REST API approach into your sort of new domain-driven approach?
Depending if you want to work, basically, you can spend 1 or 3 months. 3 months is an average that we spend for migrating one of our regular services.
Yeah. And how big was your team again?
The?
How big was your team again?
Yeah.
How big was your team?
How big?
Yeah, how many people?
Around 10, 12 people.
Okay, all right. So the other thing we do a lot, in Amazon, our big peak periods are, there's always Prime Day, Black Friday, Cyber Monday. Can you kind of share with us, we're in a similar industry. Can you kind of tell us, what you and your team do to prepare for some of your peak days? And first of all, what are those peak days?
Yeah, basically the answer is in this session is use SNS. You can maximize the usage of SNS for giving the scalability capability for them, and just be focused on keeping your external services and your database storages on time. Okay,
so it's very not much of a change from what you do day to day then.
Yes.
Okay. All right, so I guess at this point, I'll ask Luca Di Lieto to join us on stage here. So Luca is a solution architect for Twobit, which is a system that's using NL. So NL, I guess I'll let Luca tell you about NL then. There you go.
Thank you, Robert. Thank you for your introduction. Okay, let's start with a short introduction of my company. NL, oh, sorry, the presentation. Okay. NL is a major global player in the energy sector with a diversified business. It's the global first private network operator, serving 73 million end users with 44 million digital meters installed. It's also the largest energy retailer in the world in terms of customer base, with over 64 million of final customers. It's also the first operator in the world for renewable energies, with 43 gigawatts of managed capacity. It has also thermal generation with 46 gigawatts of capacity, and objective of becoming carbon neutral by the 2050. Okay, this is NL. Just a few words about me. I'm Luca Di Lieto. I'm solution architect. I work for that blue business line, and I'm one of the product owners of the system that manages 44 million digital meters worldwide. This presentation is about digital meters. So let's start with a recap of the numbers and timeline. Enel story with digital meters starts in 2001. And in 2006, Enel completed the deployment of digital meters to its entire Italian customer base. We are talking about 32 million digital meters. It was the largest smart metering deployment in the early 2000s. In 2016, Enel decided to start a new deployment with the Open Meter project of a new meter, a smart meter 2.0. Currently, we have 44 million digital meters installed with 4 million of the new one. In the next 2 years, we will install more meters, and we increase also the percentage of the new one. This is the architecture of the smart meter 2.0. In the overall architecture, we have different components, not only meters. The main are in red. So we have meter, low voltage manager, and BIT, our central system. Let's start from BIT. It's installed in cloud and manages the communication with devices, mainly collect data from them and execute configuration on them. Then we have low voltage manager. It's a kind of data collector. It's installed in the secondary step-down substation of our grid. Its main task is to manage all the smart metering tasks of the meter fed by the substation. It communicates with the central system using a 3G and a 4G communication. Fiber optic is also an option. Then it communicates with the meter using PLC and radio communication. Then we have the meter. The meter is installed in the delivery point of our grid, communicates with the low voltage manager, and it's also able to communicate with smart home devices. These are the features of the new generation of meters. Among the other features, I want to underline that meters is able to record every 15 minutes energy consumption. These data are collected by the central system and sent to the energy market. So the end user can know his own consumption profile, and the energy operator can define flexible rate tailored on the end user consumption profile. Okay, now we have set the context. Now we focus on the main challenge for the central system and how a serverless approach are helping us addressing it. We will talk about the Twobit models. That is the module of the central system that manages the communication with device, that collect data from device and process, analyze, and forward them to the external system. We will deep dive its architecture, analyzing it in the energy consumption profile scenario. First of all, let's recap the numbers of the scenario. For meter data collection, we switched from monthly consumption register collected every month to 15 minutes samples collected every day. So we are moving from 96 million raw data points per month to more than 12 billion raw data points per day. So we are moving from 32 million messages per month to almost 300 million messages per day. How did we address this challenge? We changed our architecture. We had a monolithic application, mainly based on application server and relational data store. We had some limitation on scalability. Yes, we have a cluster of application server, but just one big data store. We needed a skilled professional in order to maintain this infrastructure. And we had also a not effective cost model. So we decided to redesign it, leveraging on an AWS serverless component. We divided it into modules, and we had benefits on administration, scalability, and an effective cost model. Let's see our current architecture. We divided the application in two tiers, an acquisition tier and a processing tiers. In the acquisition tiers, we communicate with the devices, collect data from them, and pass them to the processing tiers. In the acquisition tier, we have a legacy application that we not migrated to the serverless because we had some technical constraint on communication protocols that requires long-lived threads that doesn't fit well with the serverless approach. In the final part of the presentation, we will see also an evolution for this part, a serverless evolution for this part. Then we have the processing tier. In the processing tier, we collect data from the acquisition tier, process, analyze them, and then we send to the external system. For the integration between system and tiers, we use SQS queue. We use SQS queues in order to decouple systems and tiers. But we have also persistence, because the acquisition tiers acquire data from devices, send them to the SQS queues, and then delete them from the devices. So we need a safe place where to store our data. Then we need high parallelism and high throughput, because we have a lot of messages to process, and we have also a lot of threads in the acquisition tiers that collect data from devices and send them to the SQS queues at the same time. Okay, then we process these messages with the beanstalk worker tier that mainly connect to SQS queues, get messages, process them, and then send them to our application deployed on EC2 instance provisioned by beanstalk itself. Our application processes these messages and use DynamoDB as a short-term data storage and inventory data. Finally, we deliver this data to S3 in a streaming fashion using Kinesis data stream and data file host. And finally, we query them using Redshift Spectrum functionality. So at the end, we have also an SQL data warehouse and a real-time monitoring solution. Let's see the numbers. We have almost 300 million messages per day. For our SLA, we have only 8 hours to process them. So we need a processing rate of 10,000 messages per second. Okay, this is our current architecture, and this is in production. We are working on 2 evolutions of this architecture. The first is to go fully serverless. We have a lot of serverless components, but we have Beanstalk that is not serverless. And the way Beanstalk manages EC2 instances is not compliant with our company provisioning process. Beanstalk was the best fit for our needs, so we used it. But now that we have the new Lambda feature of Lambda polling SQS, we can now migrate to Lambda, because Lambda has the same behavior of Beanstalk worker tier. So this is our new architecture. We have just started a POC on it. We can say that we had little effort in order to start the POC, and that with this POC we are evaluating also some optimization, like batching messages, in order to reduce the overall cost. Let's see the benefits. Lambda is easy to operate and easy to deploy. I say, joking, that it's a friend of our operation team. Our current mixed approach is not well accepted by our operation team. Consider that currently we have 2 CloudFormation files. One with all the servlet components managed by our company continuous deployment infrastructure, and the other one with the Beanstalk components managed manually by our operation team. This is not good. With this evolution, we will be able to manage everything with one CloudFormation file managed by our continuous deployment infrastructure. Then Lambda is easier to scale, scales fast. It adds instances when we have messages on queue. We have also concurrency control that limit the number of instances on execution at the same time. This is very good when we have some part of our infrastructure that slow down. Then we can monitor it. With the CloudWatch integration with our company monitoring solution, we're able to see some metrics of Lambda. In example, the number of instances of Lambda in execution, or the execution time. Then we have another evolution. This affects the acquisition tier, and involves also devices. We are redesigning it using AWS IoT Core and deploying on devices AWS Greengrass. So we are leveraging the low voltage manager as an edge computing component. We are moving some logic, application logic, from the center to the edge. We are also improving the overall security. For those of you that are interested to this evolution, there is another section here at the reInvent on edge computing, presenting the details of this evolution. However, I can say that with these 2 evolutions, we will be able to go fully serverless in the processing, collecting, and analyzing energy consumption profile.
Thank you, Luca. What do you think are some of your biggest challenge when you go to this next stage, like when you go from migration to Lambda? What do you think are some of your biggest challenges to get there?
But for the POC, we had just a little effort in order to change it. But I think that for the production environment, we have also to have some optimization, to make some optimization. For sure, we will have to use the batching messages. And also, we have to change our dependency injection framework in order to deal with the hot stuff, cold start, and so on.
Mm-hmm. And I know it's fairly early for you in your migration to your full digital meters. Have you been able to establish any sort of early business success you can share with the audience?
It's a bit earlier. For the business, the main objective is to meet SLA. Mm-hmm. To meet SLA every day, not just one day. So it's easy to meet SLA one day when everything goes well. But we have to meet SLA every day. Also when we have issues, and issues happen. So we have to manage it. We have to monitor our solution. We have to identify issues. And we have to have the ability to recover from it. Maybe processing the same amount of data in half the time, because you have some issues in maybe some misconfiguration, or network issues, or telco issues, or maybe that you have devices that are not sending data half the day because there are a storm somewhere. So this is the main business goal. And I think that this serverless approach can help us addressing it.
Okay, well, thanks so much for sharing your experience with us. Look forward to catching up with you later to find out how everything evolves. So I think in summary, we're almost out of time here. Just I'd like to leave you with a few thoughts. First of all, if you're dealing with a lot of bursty traffic and high throughput traffic, keep in mind, having serverless in your toolbox and the services that are provided servicely, those are good tools in your toolbox. Basically, we take care of all the scaling, so you go up and down as you need, and also you basically pay for what you use, and you don't pay for any idle resources. The other thing we also talked about is the use of message filtering. That really gives you an efficient way to design your publishers and your consumers, and making sure you have that abstraction layer, and also limiting the amount of traffic that you're pushing onward to your downstream processes, and that will reduce your cost of operation as well. And then lastly, with the SQS, the Lambda capability, that's a new endpoint capability that now gives you the flexibility to deal with bursty traffic, so you can actually buffer and slow down and use concurrency limits on the Lambda to sort of protect your downstream resources and to deal with this bursty traffic. We covered a lot of material in the session, and I'm sure that there's a lot of questions in your mind still. So I've collected a few sessions that you may want to participate in later this week. So the first one is, if you're really interested in dealing with Lambda functions and SQS queues, there's a breakout called Best Practices for Queue Processing. There'll be some senior engineers there, and then they can answer and talk with you with really high level of precision on how to use these services and the features together. If you're wondering about what message service is the right one for your application, there's a session on that as well. And do you remember at the very beginning I had the slide that basically showed you the map of all the serverless technologies as part of our modern application platform? There's a session here, the third one, called Technology Choices for Modern Application Development. That's put on by one of our principal engineers, and he'll go through in detail about each of those tools in your toolbox and give you a high-level view of how to use some of those. And then lastly, I'd mentioned that we also release VPC endpoints and also server-side encryption. So we actually have a breakout session, actually a chalk talk, where we have one of our senior engineers there working and explaining how some of those are work and how you can leverage those new features as well. So I'd like to thank you for your time. Thanks for spending the afternoon at lunchtime with us. And please enjoy the rest of your week. Thank you.